Hello, I'd like to welcome everyone to today's SWANA e-learning event, Gasification and Mass Burn, Comparing Apples with Apples, presented by Peter Kromek of Hitachi Zosen Innova USA. Everyone should be seeing a slide with the title of today's session on it. If you're not seeing the slide, or if you have any audio or other issues during the session, please call the ReadyTalk customer care line, and you'll see their number at the bottom of the slide. It is 1-800-843-9166. That phone number is also in the logins that you received to access this event today. SWANA would like to let you know about two recorded e-learning opportunities that we have available. First, SWANA is offering a recorded version of the Transfer Station Systems E-Series, which examines best practices and industry standards in transfer station planning, design, and operations. This e-learning opportunity is sponsored by Karen Compactor, recognized as an industry leader in compactor technology. Also sponsored by Karen Compactor is SWANA's Manager of Landfill Operations E-Series, also known as MOLO. It's available in full as a recorded webinar. MOLO examines best practices and industry standards in landfill management and operations, including comprehensive study of site design, regulatory and compliance issues to consider when planning and operating and closing landfills. Before we begin, a few other items. This program works best if all other programs on your computer are closed. In order for everyone to enjoy the session without distractions, your phone has been muted and will remain muted throughout the session. If you have any questions during the session, please type them into the chat box on the left-hand side of your screen. After the presentation is over, there will also be time for Q&A. To ask a question at this point, you can continue to use the chat box to ask your questions. You can also use the raise hand icon that you'll see next to your participant's name. And if you press that, that will tell me that you want to be unmuted to speak over the phone line. This session is being recorded and will be available for purchase on the SWANA store. It's also available to you for free for 1 week via a link you'll find in the post-eSession email that you'll all receive later this afternoon. And with that, I will turn things over to our speaker for today. Peter?
Hello, I'm here. Thank you very much for listening, and you'll have the good chance that you'll have a recorded session with my Swinglish accent. So I'm glad to be able to talk about gasification and mass burn comparisons. And I would just like to jump into the first screen then. So if we compare technologies in a general way, obviously we have to look at various things. One of it is obviously the criteria under which we compare two technologies or two solutions. And those criteria mentioned most in the waste management industry obviously are diversion rates or emissions, as well as energy efficiency. Also, if we want to do a comparison, we have to look at the method, how we compare two different solutions or technologies. And the method that I would like to show here is basically looking at trying to make sure that we use the same boundary limit and same assumptions for those comparisons, and we'll have a heavy focus on detailed mass and energy balances within that same boundary limit to compare various solutions and methods. And that's exactly now where I have to put first disclaimer about the content of that presentation. We are a company and do provide solutions with advanced mass burn technology. We have obviously quite good data set from our plants. These data are also, I think, very much publicly available through various operating plants that have been scrutinized by engineers and consultants. So we have a pretty good data set of these. If we talk in this comparison, if I talk about other technologies like gasification, I don't have that good data. I use data from literature. Sometimes the literature data are a combination for various technologies. So this paper definitely should not provide accurate mass balance or energy balance data of any single gasification technology, nor talk about any single gasification technology. The main focus here is to talk about the method, how we compare various different technologies in the waste management area, in the thermal waste management area, with each other. So let's first look at the first topic, which is define the boundary limits. And I think for me, it's very important that you fix those conditions for all the comparisons. And what I did in this comparison, I look at the MSW feed that we typically see as delivered from curbside collections. Then we also have to include consumables, reagents, and other utilities used, and these could be very different for different technologies, but it's important to consider all of them in the comparison. Then we have to look at the residues which go to disposal and at the recycled products. In some area, and depending on legislation, it's not always clear what products out of the system are considered a recycled product or have to be considered a residue for disposal. This depends a lot on legislation and on established routes for a certain product in the market. Then also we have to look at emissions, and it's very important here that we have to look at emissions after the work is done. I've seen a lot of people that compare different technologies and say, well, I am producing only a syngas, I have zero emissions. I don't think that's the full system that we have to compare here, because at the end sometimes a syngas or even a liquid fuel is combusted to produce the work it's supposed to produce. And in a liquid fuel situation, obviously, we have to look at the emissions at the end of the exhaust pipe of a car, if that should be a fuel-driven car, or if it's a syngas going into a gas engine or a gas turbine. We would have to look at the emissions that are produced after the gas turbine or after the gas engine. And only like this we can compare the waste-to-energy concept on an equal basis. Also, recovered energy obviously should be compared as the total net energy that's available to the grid, considering this whole boundary limit. And here it's important to make sure that we compare the energy that goes to the grid, which we can take or which we can produce from the MSW feed as delivered, and use the same parameters here. Some comparison I've seen that obviously already assume some pretreatment step for the MSW before they compare the thermal treatment portion of the plant. So again, same battery limit for all the comparisons. Now, we have to also, if we want to do a comparison, define the feed stream. And in all the comparisons, we have to use the same feed stream. In this comparison, I've used an ultimate analysis that you can see here, which is typical for some curbside collected waste. Important also to see that the heat value for any comparison have to be clearly defined or recalculated during the comparison. Also, the dimensions are an important factor. If I see usually feed that's delivered from the curbside, it can contain particles or elements up to several feet of size, can be bulky or in bags. Whereas I've seen comparisons that assumed that already the feed stream is a little fluffy RDF type treated product. Mass balance considerations obviously not only have to consider the ultimate analysis and total mass balance in terms of total mass stream, but for all the mass balance considerations, we also have to look at component mass balances. We will go into a little bit further details about component mass balance considerations. Important here is that for every component or contaminant that we have in the feed stream, in the waste stream, and we have them, we cannot just choose not to have them. We have to know for each step what are the distribution coefficients, why would that contaminant go this way or that way. And so at the end we know where these contaminants end up in the process. And I've seen one question, LHV stands for lower heat value, which is typical the method used in Europe. And HHV is the higher heat value, which is typical the method used here in North America. Now, for energy balance comparisons, it's very important that we use those exactly those heat value numbers. If we look at an LHV basis, basically the LHV basis assumes that at the end of the process all the water is still in a vapor phase, although the energy basis for that comparison is typically either 0 or 20 centigrade, which is 32 or 40 Fahrenheit. That's typical, the comparison temperature level for all these energy considerations. So actually water would be naturally in its liquid form for this comparison. But since for energy purposes, normally the water is always in a gaseous form in the flue gases as a vapor. The LHV concept just assumes from the beginning that the water for comparison method is not considered to be in a liquid form but in a vapor form. So comparing on an LHV basis, these 9,600 kilojoule per kilogram would translate directly to 2,427 kilowatt hours energy per short ton of waste. So again, if I look at those numbers, and if someone says that this is a number very frequently used, someone can produce either more than a megawatt hour per ton of waste, then that would mean with this waste that we typically receive from the curb, that would correspond to 41% total net energy efficiency. And obviously we can compare that with cold gas, syngas efficiencies, and with typical efficiencies of energy machines like either gas engines or gas turbines. But already with those efficiencies that we see, if someone wants to create 1 megawatt hour from this particular ton of waste that I'm looking at here, that would mean that the process efficiency would already have to be very, very high. So be careful. If someone just says, I can produce a megawatt hour per ton of waste, it's very important to look at the assumption, what waste has been assumed, and what the heat value of the waste has been assumed, and what other assumptions are considered. Now, let's start first with a modern mass burn example. We have built in 2011 a unit in London, Riverside unit located next to the Thames River. It has 3 lines, combustion lines, each about 840 tons per day. It uses the MSW as delivered and collected by the collection vehicles in the city and area of London. They bring it then at the transfer stations. They bring the waste onto barges on the Thames River. The barges deliver it to the plant, and it generates steam. Generates electricity. It's prepared for cogeneration, so in the future also steam could be used, but at the moment this plant produces about 73 megawatt gross, can sell about 65 megawatt to the grid, which corresponds to 662 kilowatt hour per ton of the same typical MSW I've used before as a basis for all those comparisons. So let's now go a little bit more detailed in these mass balance comparisons, and always like to see graphical comparisons like the Sankey diagram comparisons, which I find very helpful. As an introduction, the mass balance here is all based on percentage numbers, and the percentage are standardized such that we use all the waste feed that goes into this plant in tons per hour or pounds per hour, representing 100%. So all the mass streams in this mass balance are relative to all the waste stream, feed stream being 100%. So a very easy example to follow that rule is look at the pre-treatment, which in a mass burn plant is actually no pre-treatment because the mass burn plant takes the waste as it's delivered. So this treatment has 100% in, 100% out, no change in the mass stream. If we go to the thermal treatment then, or the total treatment system, we have to look at the few additives that we take in. Typically this is ammonia for NOx control, or it is lime for acid gas control, lime going back here into the gas treatment, typically the ammonia going here in the thermal treatment. That's this part of the mass balance here. Look, I can skip this. Look at the next part. An interesting thing in mass balance terms of view, this little loop that you see here, that is basically the flue gas recirculation that we use in our process. So after the gas treatment, we take part of the flue gas and bring it back into the thermal treatment, which looks a little bit funny here on a Sankey diagram. But this is explanation for that stream. Also, you can see that there is basically a big air stream going into the thermal treatment to be combustion air, and we also have a little air stream going into the flue gas treatment. This is typically all used for either injection of additives or for some cooling or for back purge of the bag filters. That's typically this airstream here. Another thing that you can see here, if we do the water balance, in this case we have only a very small water feed stream, and those looking at the technology in more detail will immediately see that obviously we are using an air-cooled condenser here, because otherwise the water stream, water consumption, if we'd have a water-cooled condenser, would be much larger. Next thing I would like to look at a little bit more is the whole residue treatment. Here, typically, we would have about 25% of the mass of the waste coming in, leaving the thermal treatment in the form of wet ash. We'll have another 3 or 4% of the mass leaving the gas treatment as gas treatment residues. From the wet ash in the residue treatment, we typically would take out about 2/3 of the metals, which go to metal recycling. In some plants, this is done either at the plant. In some areas, also, the typical metal recycling is done at the landfill. So metals are recovered from the mass burn ash. The rest is typically going to disposal. This is the total mass balance diagram for a mass burn facility. Let's now go to the energy mass balance, and you'll probably see, and if you compare to the previous stream, I go back again to the air streams here, where you see that the air streams are the biggest streams in terms of mass. You will see on this Sankey diagram for energy balance that here the air stream at ambient temperature actually contain no energy. So again, this energy balance is based on a lower heat value basis. So it's made under the assumption that the water in the waste is just reducing the heat value, and that the water vapor in the flue gas stream contains no energy. In this case, we have the waste trucks coming in with the waste, and again, we normalized the energy content of all the streams, the energy streams in the whole system here, such that all the energy, the chemical energy content of the waste is 100% of the energy. And so in this case, we also have the chemicals again. In this case, we considered the chemicals energy content is close to zero. They are at ambient temperature, and the little chemical energy contained in, for example, the ammonia which will react is assumed or neglected in this case. There is no pretreatment, so again, the chemical energy in the waste stream is the same after pretreatment. And if we go into the mass burn, then we typically have part of the energy content that leaves with the flue gas into the gas treatment and to the stack. And we have the rest of the energy, most of the energy that's taken out by the boiler into the water steam system, water steam cycle. In the water steam cycle, we have a turbine generator, which in this case can take out about 31% of the energy, while the rest of the energy leaves the system through the air-cooled condenser, about 52%. To be considered as well, if we look at the ashes, we have seen that there is a big ash stream in terms of mass. It's about 24%, but since that ash stream is basically all combusted, and we have a non-combusted matter or organic content in the ash stream of something like 2%. This is part of the energy which is still leaving the plant with the ash stream. The other part of the energy is obviously about 1% of thermal energy in the ash stream, which obviously is because the ash leaves the plant at the elevated temperature of several hundred degrees and needs to be typically quenched by water, and that would be a dissipation loss. So here again we have a few percent loss with the ash stream, most of the loss with the air-cooled condenser, a considerable loss still at the stack with the still warmer temperature flue gases, and in the end 75% of the energy contained in the waste is available to sell as power in the grid. 31 here you see generated a generator, but then we have those typically 3-4% electrical energy as electrical energy, which is the parasitic load, which goes back to the crane or goes back to the thermal treatment and goes back to the flue gas treatment. So 75% is basically the electrical energy that can be sold in percent of the total chemical energy available in the waste. Then, as a next example, we have used a few technological improvements that we did in the past, and which we will apply to one new plant to be built in Lucerne, Switzerland. That allows us to further reduce the excess air, also further increase the energy efficiency. Also, we have used some other concepts, the Thermoread concept to this plant in the UK, where we would propose a dry bottom ash extraction, which allows to further reduce the energy lost with the organics in the ash, also further cooling the ash, so reduce the thermal energy losses with the ash. We also increased the metals recycling rate with this concept, and we assume in this case that even the mineral fraction of the ash can be, at this example, recycled 50%, which is today possible in certain legislations, but not in all. So that's kind of very much depending today on the legislation, whether the mineral portion of the ash can be beneficially used or whether this has to be considered a residue that goes for disposal and therefore doesn't contribute to the diversion rate of the whole process. So again, if we apply those two recent developments to our UK unit, we'll have again a very similar mass balance diagram, however with a few little changes. One change is that, as I mentioned, because we can reduce the excess air for combustion, we'll have lower amount of air needed. We have a lower amount of flue gases leaving with a stack. While this number was 660% in the previous example, we have only 570% total flue gas stream mass flow compared to the total waste mass flow. Also, I mentioned the thermory concept, which obviously allows some changes in the residue treatment area. So while last time we had only 2% metals recycling, we assume here that we can recycle virtually all the metals, certainly 90% plus of the metals contained in the waste stream. Also, we assume, as I said, that we can recycle about half of the mineral fraction, which, however, as I said, needs to be confirmed and may be different from country to country depending on the legislation. This would kind of be the mass balance diagram of such a modern mass burn unit. Let's go into the energy balance side of it. If we look at the energy balance of a modern unit, we would see that the stack losses here could be reduced. As I said, we have less excess air, so with less excess air and less mass flow going through the stack, we also have less energy losses, thermal energy losses through the stack. Because we have less excess air and less flue gas flow, we also have a lower parasitic load going back to drive the fans in the flue gas treatment. If we continue here in the residue treatment, because we can recover the ashes in a dry form and recover some thermal heat of the ashes, we have less energy losses with the ashes. We have also less energy losses because the burnout is better and we have less chemical energy or less organic materials in the ashes, which in a normal waste-to-energy plant are maybe only 2 to 3%, but with this technology you could typically go down to 1 to 2%, which all can be at the end measured. So looking at all the little improvements on the parasitic load, on the losses of with the flue gases, and the losses that we would have with the ashes, this would be now an overall electrical efficiency up from 27.5 to 28.2% electricity available to sell at the grid, compared to the chemical energy contained in the model waste that I've assumed for all those comparisons. And if you want to use that number here, the 28.2%, in a comparison with other processes, there is one plant in the Netherlands, AVI Amsterdam, which has used many technological little changes to try to optimize the energy recovery. So they use a more sophisticated water steam cycle with intermediate reheating of the steam and the higher pressure, higher temperature of the steam. And they use variable speed drives in all their own plant and consumers, so they can reduce the actual electricity consumption. They achieve, I think, overall electricity production to the grid of a little bit over 30% compared to the energy contained in the waste. So that is about the level that a modern mass burn can achieve for a total system. And again, total system means waste as delivered from the truck, until the power grid. And also here, I think there will be improvements possible with the future, but that's about the level we are talking at today. Now, I mentioned at the beginning that we don't have to look only at mass balances in terms of total mass flows, total mass streams, being where does my 1 ton of waste end up, but we also have to look at the component mass flows if we compare different systems with each other. There has been a pretty thorough analysis of the total mercury system in Austria recently. And they have looked at just mercury. Where does mercury enter my country? Where does it leave the country? Where does it leave either to the air or to any landfill space? And they have figured out that about 10% of the total mercury they have in the loop in Austria at the end somehow ends up in municipal solid waste. So there is an amount of mercury coming in with your curbside collected waste. If I recalculated that, it would be probably some 100 milligrams per ton of waste if you average it out. But whether you want it or not, that mercury will be there in your waste. And it's very important if you do comparisons between different solutions that you also follow components. And so I've made the same comparison here, which I did before on a mass stream basis for a total waste mass stream, only for the mercury. So again, no pretreatment means no change in mercury content. 100% of the mercury continues to the thermal section. Now, at the thermal section, again, thermal treatment, you have to look at where does mercury go. And typically, and I just use very round numbers, they don't need to be absolutely correct. Most of the mercury, however, in a thermal treatment process involving high temperatures will definitely leave the thermal treatment process with the gas form, with the flue gases. Next step then is flue gas treatment, and you'll have to look at what type of treatments you have, in what form the mercury is, and you can assume that maybe most of the mercury in the flue gas treatment is captured also because of the emission regulations for mercury. So in this case, about 96% of the mercury that comes in with the waste stream is available for disposal in a modern mass burn facility. And that's probably also one question that we have to ask ourselves very general form. We cannot, until we have redesigned all products and if we have banned mercury from all applications, and obviously there are also in that area there are conflicting goals. If we want to reduce our electricity consumption, and if we produce light bulbs that reduce electricity consumptions, and these light bulbs contain some traces of mercury, then maybe the bigger benefit is reduction of energy, and we have to assume that there will be some mercury in the loop. And we also have to assume, for just practical reasons, that not all of that mercury can be taken out of the loop by appropriate recycling and disposal. And some of the mercury, like the Austrian example shows, in this case 10% of the mercury they have in their total system ends up somehow in the municipal waste stream. So the question is, if we find other processes like this one which somehow manage to take my waste stream and divide it up all into different products, and at the end almost have no 100% diversion rates, that would mean that obviously also all the mercury ends up in one or the other of those products. And that's a question we have to solve in the whole waste management industry. As long as we have some contaminants here, they have to end up somewhere. And with, for example, a modern mass burn unit, there is the possibility that you will certainly take the majority of those contaminants out of your loop and bring it to a controlled disposal at some place. Now, a lot of the comparisons, technology comparisons also have some link to Japan because the Japanese, for many reasons, use a variety of technologies, and they also use a lot of gasification technologies. Most gasification technology plants actually operate in Japan. So we have looked at one of the gasification melting systems that we know a little bit better. It's not a one-to-one comparable with our comparison before, so we had to make some adaptations in terms of the assumptions regarding waste, assumptions regarding so it's comparable. But typically that unit is very small, like most or all of the Japanese gasification units are very small units. This one treats RDF, which is pre-treated, so it's not curbside collected waste. Pre-treated, pre-dried. So a lot of the inerts contained in the raw waste as you get it from a curbside are already eliminated. So for this comparison, we have considered also literature data of one of the RDF processes, and this plant also uses melting technology to melt down the residues they still have in the end. So they have an inert ash or inert slag. At this case, and also probably because the unit is very small, we didn't assume that the slag is further separating metal fractions and inert and mineral fractions from the slag. But this would be the process to look at. We have, in this case, we have a pretreatment, and the process technology used for that gasification melting plant requires a pretreatment. That pretreatment needs drying, so a lot of the humidity and possibly some organics with the humidity, you cannot avoid that, will leave the pretreatment to the air. And again here, if we make a comparison, for example, on a carbon footprint basis, then we'll have to look at how much organics are leaving here and what's the carbon CO2 equivalent factor of those. Then they typically have a waste stream that's only about 50%, but since they have to remove the big and inert pieces, they have a stream that goes from the pretreatment directly to the disposal. So we have to look at these inert residues here, and these residues have to be considered if in your diversion considerations. You cannot only look at the treatment step here, the thermal treatment step. Then if you look at generally the flow sheet, you will see that probably flue gas amounts are similar because they take most of the energy content into the thermal treatment. They also have similar flue gas amounts. The ash, as I said here, is molten, so the molten ash or slag can all go to recycling. It is assumed to be an inert slag which can use to the construction industry. The only thing we assumed here is that since they have all the contaminants in the flue gases and have to have a flue gas treatment which is similar to us, we've assumed that the ashes they bring out from the flue gas treatment will have to go to disposal somewhere too. So that will provide the diversion number for this gasification melting process as a whole process. That's what I just explained before, just including the two arrows explaining it. Going into the energy consideration of this process, we have assumed that the pretreatment actually is able to carry 95% of the energy into the thermal treatment, which, as I heard in the past when I discussed with a few people, is a very ambitious number. A lot of the pretreatment, I've been told, will not achieve 95% of the energy content of the waste coming in, ending up in whatever RDF or however you call it, the product that you will bring into the thermal treatment. So this is an optimistic number here. Also, can you see as a difference, the pretreatment consumes electricity. So we had to use an average number for the pretreatment as an electricity consumption, which definitely reduces the energy available for the grid. We have another thing that we would like to look at here, the plant in Japan is a very small plant. So as a very small plant, it has a turbine generator as well, but the generator efficiency for a very small plant is rather low. This is one of the reasons why many of the Japanese small plants are operating actually at very low electrical efficiencies. Not only because they have other inefficiencies here, but because of the size of the plant, turbine efficiencies drop very fast. So this is one of the explanations, obviously, in addition to the higher electricity need in the pretreatment, and also in addition to the lower efficiency of the turbine generator used. That's one of the reasons why electrical efficiency is rather small. But generally, if you compare mass burn and gasification units, there also seems to be some technical limit with many of the gasification technologies, which doesn't even allow them to build larger plants unless they just duplicate gasifiers. So I don't know how much this is just a structural limitation that in Japan many plants are very small because they have small communities and the small communities need their own disposal method, or whether that is at the same time some technical limit that thermal plants that have a partial gasification or melting step, that they are probably better smaller than larger. But this is the overall electrical performance of that step now. So going to the plasma gasification syngas cleaning gas engine process that I wanted to compare on the same basis. And again, please remember my disclaimer at the beginning. This is not one process. This is a hypothetical or theoretical process established from various data we found in the literature. And probably this is one of the problems if we try to compare those different technologies, that the literature data or data available of those processes is pretty scarce. A lot of the technologies are operating on a kind of proprietary, secret, technical new technology approach. So obviously those numbers cannot be scrutinized to the detail, and you are pretty much depending on what the people offering those technologies tell you. But to compare with other plants, also here we have included a pretreatment step, since most gasification systems need a thorough pretreatment and size reduction. We have found one technology or two technologies that require some carbon source additives or flux material additives. They have different names. We've included those. We have seen that some technologies operate with oxygen rather than air as an oxidation agent. The residues in this case are assumed molten, inert, and suitable for recycling. So we've assumed that all metals would have been recycled and separated here. And we also assumed that some residues from syngas cleaning need to be landfilled at the end, although that's the most difficult part to find in the literature. It seems that the biggest challenge for gasification, if you want to go into a gas engine, and that's probably also one remark here, I don't compare or don't look at those gasification technologies separately which directly combust the syngas in a boiler, because that's basically a stage combustion. This here should really be a comparison with technology that has a better use for the syngas, which in this case could be a gas engine or could be a gas turbine later or some other technology. So the syngas cleaning required for making the syngas suitable for gas engines or gas turbines is the biggest challenge. And obviously there's little data, but again, if you want to take all the heat and the chemical energy in the waste, then you also have to take all the chlorine and the sulfur and the heavy metals load in the waste. So we have assumed that some of that has to be removed as well in syngas cleaning. So again, what I said before, if 100% is the waste stream, we have, in those cases, we have an additional carbon source or chemical requirement for the thermal treatment step. also some chemicals, obviously, and we've assumed in this case probably the same amount of chemicals needed for the syngas cleaning to get all the contaminants out. We have, and this is true, this is one of the aspects which many gasification people say, that if you compare the total gas volumes that need to be handled in a gasification process, this is in this case only 80% of the waste mass flow. While if you look at the same diagrams before for mass burn, the main process deals here with 500% of the mass due to the big amount of air needed for the thermal treatment step and the gas treatment step. But if you look at the overall picture in terms of emissions, then you see that latest when you want to have the syngas do the work that it's supposed to do, or if you want the fuel do the work that it's supposed to do, then latest at the gas engine or the vehicle or any other step, you will need that air again, and you will have flue gases of a similar magnitude, 550%, 600%, at the stack. Although obviously I've heard people that differentiate and say, well, in their case this is an exhaust pipe, not a stack, so you have to differentiate. But if you look at the mass balances and if you later look at the component balances, I wouldn't make a difference between a stack and an exhaust pipe. Next question is ashes and residues. As mentioned before, since some of the gasification processes would include melting of the solids. That would include here maybe 10% here, which can go into recycling as a slag, which if they take metal out as a liquid form, that would go into recycling as well. But again, if you look at the overall diversion rates, don't forget that the pretreatment very often needs to remove some materials. And if you combine then the pretreatment residues and the residues from here potentially assumed from syngas cleaning here, then you will also come up with a similar amount of products to be disposed of in some way. Next thing is a component mass balance. Again, it's very important that you look at the whole picture. As I said before, whether you want it or not, you will have some mercury in your waste stream coming from the curb. So what would a pretreatment do with the waste stream? I have to put question marks here because I have no idea at the moment how much of the mercury would leave with the vapor from a pretreatment where the waste is dried. I don't know how much of the mercury would be going with the solids that's separated. I think this would probably be rather small, and most mercury would go into the thermal treatment step. Next step, if you have a thermal treatment, if people tell you that first of all you ask the question, well, how do you assure that you get all of the chemical energy of the carbon out of your thermal treatment? And then the response is that they have very high temperature, or they have plasma assisting the whole process with very high temperature. Then that would be a reason for me to believe that you cannot at the same time have all the mercury go with the inert slag. This will mean the mercury will go into the gas phase as well, into the gas treatment. And then from the gas treatment, the question will be how much of the mercury can be captured, what form in a gasification is the mercury present? Is it metallic? Is it ionic? Is it attached to some particulates, or is it just a pure gas form? And then also, depending on that answer, you have to find out why would mercury in the syngas treatment go that way or go that way. So in the end, in order to have the overall component mass balance picture, you have to know a lot of more details about processes in a thermal treatment gasification as well as in the syngas treatment. But still, there is a question that the exhaust pipe, as they call it, will also become a stack and will also contain mercury and will need to be regulated under appropriate emission regulations. Energy now is, again, questions that you can ask. Can you get 95% of the energy into the waste material that goes into the gasification? Very important here is that also the additives, as they call it, either flux material or carbon source or other things, that sometimes they contain a very significant amount of energy, chemical energy. In this case that I've looked at the end, the hot syngas would contain even 107% of the chemical energy compared to the waste at the beginning. This is not because they made something very fancy with the waste, but this is because of all the energy content of their additional carbon source that comes into the thermal treatment. So then again, you have cold syngas efficiency that you have to look at depending on the process. Then obviously the syngas will very often need to be quenched, so you have a dissipation loss for quenching syngases. You have dissipation losses because you have to cool a plasma torch, or because you inject some other media in here. You have dissipation losses in the pretreatment, where you obviously lose some VOCs with the gas. Then, and that's the very interesting thing, obviously, the efficiency, the electrical efficiency of a gas engine is very high. In this case, I've assumed the 37.5%, and I realize that obviously there are new developments that you could combine an ORC cycle to capture additional heat from the exhaust pipe of your gas engine, or maybe you can use in the future a gas turbine for the syngas, although the question is always, is the syngas clean enough to do that? But if you make the balance now with the 37.5%, which is a number I found in literature, as the electrical efficiency of a gas engine for syngas, then you would end up with that much electricity if you subtract the electricity required for the gas treatment and for the plasma torch and for the pretreatment and so on. So if you look at 26.3%, you could say, well, that's great too, but this is obviously the energy, electrical energy that you can get out compared to 100% waste if you add first 16% of energy in a carbon source. So if you take that out of the consideration again, that you would subtract again the energy coming in from a carbon source, then in this example you have only 22% electricity coming from the waste and available at the end for the power grid. Again, with improvements here, adding an ORC, I think that number of 22% can also come to the area of 30%, but that would be the number I would make with an overall comparison. So let's compare those few technologies, modern mass burn and some advanced technologies. Diversion rates. Today, a lot of the diversion rates for mass burn are looking at the 70 to 80% on the assumption that you cannot beneficially use the mineral fraction. I think there will be technologies that would allow to at least partially use the mineral fraction. In some countries in Europe, mineral fraction today is reused. So the diversion rates can certainly go up to far above 80%, close to 95%, if you assume that you need the residual final 5% to dispose of the contaminants that you have in the waste stream. Also, the gasification technologies, if you look at the pre-treatment requirements, and if you assume that there are still some residues from syngas cleaning, they are in the 80% plus minus range. The recycling of the metals today is obviously rather in the 50-70%. With our thermal concept, I think we can certainly get above 90% metals recycling. Gasification, of course, you can do metals recycling over 90% today if you look at also separating metal melt. Emissions from a modern waste-to-energy plant at the stack, about 6 tons of flue gas per ton of waste. If you look at at the gas at an exhaust pipe after the syngas has done its work, you will also end up at the order of magnitude of 5-6 tons of off-gases from your whole overall process. Energy efficiency at the moment, I think 25 to 30% electricity to the grid is a very good assumption. If I look at the new thermal treatment processes, and if you look at the total system with the same type of waste, then today I look at numbers of 20 to 25% electricity to the grid, although I mentioned with an ORC, I think 25 to 30% is definitely also possible. The assumption that you can use a gas turbine or a combined cycle with syngas will depend very much on how clean you can get the syngas, and I think this is the biggest challenge here. Main losses, again, these are just the numbers backing up the electricity to grid number I was explaining you before. The challenge is on the mass burn side. I think we can certainly get some more percentage with a more efficient steam turbine cycle, maybe higher temperatures, higher pressures. That would require other materials of construction, because there we are in a challenge with the corrosiveness of some contaminants that are just available and present in the waste. But the same is true for the syngas treatment. I think at the moment the challenge is still that the syngas, in most of the cases, with the contaminants we have in our waste, will be not necessarily good enough yet for all gas turbine applications. All in all, conclusions, I would think the term advanced should not be used only to non-mass burn technologies. If you look at the total system, modern mass burn technologies today, if you look at whatever comes out at the stack, whatever the energy efficiencies, whatever needs to be still landfilled or deposited, has absolutely comparable diversion rates, emissions, and efficiencies like what many of those who call themselves advanced would be able to achieve. One conclusion is that at the moment we still have very little reliable independent data about many of those gasification processes proposed. I've seen there are some 180 technology companies out there, but we have to get more information. We have to, at the end, be able to exactly draft those Sankey diagrams for material flows and for energy flows for all those technologies, and then we can compare them on a same basis. And just as a little remark, just hearing about this 1 megawatt hour per ton electricity per ton of waste, without knowing all the background and without being sure that you compare it on an apples-to-apples basis, this is just not true. Also, all the zero emissions claims of modern advanced thermal technologies, they are just not true if you compare them on an apples-to-apples basis. Again, mass burn, advanced mass burn is a ripe, juicy apple. It's proven, it's clean, it's efficient, it operates more than 8,000 hours a year, it's bankable. While on the other side, new thermal technologies, sometimes you could still call them green in terms of not fully matured and proven yet on an industrial scale. If you compare those two technologies, you have to be careful that you are not comparing only part of the apple with the full apple in certain systems. And if you compare them, you also have to make sure that you'll not find a technological worm here or there in terms of assumptions or claims that are made which are not yet proven on a technological scale. That would conclude my presentation for today, and I think we are pretty much in the 1 hour range and could probably open the microphone for some 15 minutes of question and answers.
Sure. Thank you so much, Peter. It looks like there are a few chats that came through while you were speaking. I'm not sure if they were addressed or not in what you went over. But the first one is from Andy Comstock, and he asks, what is LHV and HHV, what do they stand for?
Yes, I think I tried to answer that. I saw that LHV is a lower heat value, HHV is a higher heat value. The main difference is that on the HHV concept, you really assume that the baseline you compare is the ambient temperature comparison, and the water at the ambient temperature is liquid. In most energy applications, you will not be able to condense the water vapor out of the flue gas stream, and therefore the lower LHV, lower heat value concept, has been established in many energy-related concepts. And this system assumes that the energy of water evaporation is already reduced. It's removed from the energy content of the waste. So the waste is assuming the waste energy content is already made on the assumption that the water either available in the waste or the water generated through combustion of hydrogen will remain in the vapor form.
And there's a question from Ali Abedini. So is the 27.5% energy overall energy recovery efficiency?
The 27.5% really is the amount of energy you can sell to the grid as electrical energy compared to the chemical energy amount in terms of lower heat value available in the waste. That's the I've learned some exergy studies many years ago, and I'm not sure if I still fully understand the concept. Obviously, the 27.5% of energy available as electrical energy has a very high value, almost highest value of energy. Obviously, if you have energy available as a low temperature heat, that energy is not very valuable because it's just a little above ambient temperature. So you can really get 27.45% electrical energy from the total lower heat value chemical energy available in the waste. I hope that answers the question more or less.
Okay. Yes, Ali commented in the chat box as well. Same concept, exergy equals work done at the end equals electricity for grid. Thanks.
Okay, great.
And Ali also asked, can you also comment on the capital costs for these two apples? How do they compare?
That's very difficult for me. I really don't know the capital cost of the later, newer proposed technologies. The only important thing is that I can say is obviously even in a modern mass burn plant, if you look at the total capital cost of such a plant, then a lot of it is really associated with the overall building, the overall waste bunker, the waste crane. And if you really want to move a couple of 100,000 tons of waste a year, then you need that infrastructure anyway. And it's a smaller portion of the, still considerable obviously, but not the big portion of investment required for only the thermal part of a mass burn plant. So I would assume at least the infrastructure part of any other gasification technology must be very similar cost. And then obviously you will have some differences in terms of cost for the pretreatment. That shouldn't be forgotten. Then you will have, as I said, you will have much smaller syngas flows because at the syngas level they work with much smaller volumes. But then you will have the gas engine at the end. You will probably have even some flue gas cleaning steps required after the gas engine. So I cannot compare those numbers because I don't know the investment numbers of those hypothetical gasification technologies.
Okay, and another question that we have in the chat box is from George Glenn. George asks, would it be possible to recirculate the flue gases to prevent airborne emissions and boost efficiency?
Well, the main reason why we have so big air streams or flue gas streams is that the oxygen is needed as to basically combine with the carbon and the hydrogen and all the energy containing elements in the waste. So we have to have that oxygen source from somewhere. As I said, some gasification concepts use rather pure or enriched air, so exactly in order to avoid carrying that much of nitrogen through the whole process. So flue gas recycling in our area basically will have some energetic and some emission-related advantages, but it cannot be used to avoid having a big air or a nitrogen stream bringing in the oxygen into the plant. And there have been many studies whether at the end reducing the plant size by using more pure oxygen, and I don't think that this has been viable concepts. That's why today's technology still work with air.
And a question from Andy Comstock. What is CHP and ORC?
CHP is a combined heat and power, which means that after a gas engine, there is still some energy in the exhaust gases at a higher temperature level that could be more beneficially used if there is a consumer, obviously, in the area. And ORC is an organic Rankine cycle. There is an organic, basically, it's not a steam turbine process. It's a process using organic material that's often used now to utilize the energy, the thermal energy in smaller applications and create some additional electrical energy. So that's all add-on systems with which you can probably utilize some more of the thermal energy in the exhaust gas from a gas engine and create some more electrical energy in the ORC case, or to create some more beneficial use in the combined heat and power case that you have such a power consumer, an energy heat consumer.
And we have a question from Gareth Earl. He asks, what was the capital cost on the Riverside mass burn project?
Yeah, would be a good thing now to know by heart. I'm just trying to click on my computer and see whether I can find the number very quickly. Total investment I heard was about 400 million euro. I see one more comment here. The energy balance for mass burn include the fuel used to power the incineration process. This is something which very often is misunderstood. The mass burn plant does not need any fuel to run. Typically, there is a fuel consumption because in today's legislation, it's required that you achieve all operating temperatures and residence times before you even add the first pound of waste. So to heat up during the startup, there is some fuel demand, and obviously then to cool down, there is some fuel demand, but that's negligible over 8,000 hours of operation during the year. So with typical Western, let's say Western waste, there is definitely no fuel needed. I know of a few countries which really have a very, very low heat value fuel. If you are assuming that at the end the waste is consisting more and more and more of organics and less and less of packaging materials, for example, then there are countries where you might need some fuel, and maybe in China, in some areas, they are adding some coal to the waste, but this is not at all required anywhere in Europe or in North America.
Okay. Well, we can wait a few moments to see if there are any additional questions. I can just remind everyone that there will be a copy of the recording available in a link that you'll find on the right-hand side of your post-eSession email that you'll receive this afternoon. There will also be a PDF copy of the slides from today available in that email as well. And there will be a short survey that will pop up whenever this event is over, and we encourage you to please take that and provide us with whatever feedback that you have. And it doesn't appear that there are any further questions at the moment. I would like to thank everyone who joined us on this call today, and thank you for all of your great questions. And of course, I would like to thank Peter Kromek for speaking today. Thank you so much, Peter.
You're welcome. Thank you.
And I'd also like to thank Nina for her lovely worm.
Thanks. I'll tell her.
I want to wish everyone a great rest of the day and a wonderful weekend, and I hope to see you on a future e-learning event. Have a good one. Bye-bye.
Bye.